So let's look at expected value. It's a whole lot easier when you have a binomial distribution. Okay, so the first thing asks us to go back and do some things that we've done previously. So we want to suppose a couple has 3 children. Find the probability distribution. Now that was a table or a graph. Find the probability distribution for number of female children and then find the expected value for the number of girls they would have. So we're going to think back to probability distribution. So the probability that we have 0 girls is 3, choose 0. Now, you're either going to have a girl or a boy. So your X or your R is 1/2 for a success. This is for a girl. And then if you go 1 minus a half, which is just a half, same probability for a failure or you have a boy. And not that it's a failure to have a boy and a success to have a girl. It is just that that's the way that this model was designed. Okay, so I'm going to take 0.5. This is no girls. And it is binomial, so this is 3. This is 0. 3 minus 0 is 3. When I do that math, if you do it in decimal form, it's 0.125. If you keep the fraction, it's an eighth, and it's really not a bad fraction. Okay, let's look at the probability of 1 girl. Remember, we're making a probability distribution. So we've got 1 girl. Okay, and the others are not girls, which are 2 boys. So this is 2 plus 1 is 3, or 3 minus 1 is 2. That's going to be a 0.375, which is also 3/8 if you're looking at the fraction. So we got 3 children, choose 2 to be girls. 2 plus 1 is 3. I always check that. Made an error in an earlier problem because I was writing the wrong number down, and I didn't check for the addition. That also is 3.375, which is 3/8. P of 3 is 3, choose 3 girls. So that's 3 girls. That's no boys. That is 1.25, and that also is an eighth if you're interested in the fraction. So the probability distribution, okay, this would be the number of children or the number of girls. So I can have 0, 1, 2, or 3 out of the 3 children proposed. So my probability, whether you put that in fraction form or you put it in decimal form, just depends on what you're doing as to what looks best and what is convenient. So there's your probability distribution. We're not going to graph it. It's good enough to have the table. So 1 corresponds to an eighth. 0 girls corresponds to an eighth. 1 girl corresponds to 3/8. 2 girls corresponds to the same 3/8 probability, and 3 girls corresponds to the 1/8 or the 0.125. So we've accomplished that part of the question. Then they want us to find the expected value of the number of girls they would have. So if we go back to expected value, this is the number of girls when there are 3 of them. So remember how we do that. We take our number, remember that looks like this. It's the summation of the number times the probability function. So we've got 0 girls is, I'm going to go fractions just because it gives people hives. We've got 1 girl at 3/8 probability. We've got 2 girls at 3/8 probability. And we've got 3 girls at 1/8 probability. Well, when we multiply, that's going to zero out. That's going to be 3/8 plus 6/8. I didn't cancel and simplify here because I need everything in eighths. This is going to be 3/8. So that'll be 12/8 which is just 3/2, which is 1.5 girls. Okay, so with your expected value, you're going to have, in the long run, a couple can expect to have, on average, remember expected value is kind of an average, on average, 1.5 girls of the 3 children. I think it would have been better to say of 3 children, 1.5 would be girls, would be best. See, I'm the queen of editing. I always have to write something down and then go and edit it. So yeah, I would say in the long run, a couple can expect to have, on average, when they have 3 girls, they would have on average 1.5. 3 children, 1.5 of those would be girls. Sorry, I'm getting a little tongue-tied here. So that's what we learned early on in this chapter. So the cool thing is this. Could there have been an easier way to find the expected value of the number of girls? Yes, there is. So here's the key, though. You have to have a binomial experiment or a binomial distribution to make this expected value very simple. So really all you have to do is take the number in your trial, and in this case, n is 3. You take the overall probability. That probability is 1/2. All you have to do, so this is the number of girls of 3 children. Okay, so you're going to take 3 times 0.5, and when you multiply that, you're going to get 1.5, and you'll get exactly the same thing with exactly the same meaning as you got there. So, and again, it should make sense that over the long run or over the long haul, the chances would tend towards the probability of a single trial. So you're just looking at one thing, and that is statistically sound. Expected value. So let's work this last page, and we'll kind of combine everything that we've done. So you'll have several examples. So we've got the national student loan default rate for students who graduated in 2013 is 11.3%. If 10 students from that cohort or that group are randomly selected, find the probability of the following events. Now, this is a binomial distribution. We have a given probability. We have a specific number of students. They either defaulted or they didn't. They did or they didn't, so I have only 2 things. That's what binomial means, 2 outcomes, okay? And this is a random sample. So this is a national student loan default, okay? And we are selecting at random. So it is binomial. So we want to find the probability that exactly 3 students defaulted on their loans. 3 out of the 10 that we have selected in our random sample. So 3 defaulted. Okay, so now this is a success. This is what I was talking about earlier in my first video. This is set up on default. So this probability is on default. And that is the success that we're looking for. Okay, even though it's not a positive thing, it's a success in this trial. So I've got 10 students in the trial. I'm going to choose 3. My probability is 0.113. I have 3 students there. Remember, that's your X. And then I have 1 minus 0.113 to the 7th. 10 minus 3 is 7. Let me just write that up here. Is 7. So when we calculate that, let's just do it so I can maybe catch any errors if I made any in my previous notes. Okay, I've got 10, turn on the calculator, 10, choose 3 times 0.113 raised to the 3rd power times, open it, I'm going to go ahead and make me feel just a little better. Put a times here, parentheses, 1 minus 0.113, close that parenthesis, and raise that to the 7th power. Oh, happy day. I got the same thing. So that probability is 0.0747961. So if we want to round to 4 places, that would be my probability that 3 of the 10 defaulted in a trial. Okay, so at most, 3 students defaulted on their loans. That means 3. I could have 2, I could have 1, I could have none. So this is what this looks like. At most, 3 students could be written that way algebraically, or you can just put the words. So what I know that means, it means that 0 could have defaulted, or it means that 1 could have defaulted, or 2, or 3, okay? So we have to add those together. Anytime you have that at most scenario, you're going to add those probabilities. This one, I actually ran out of space of places to key in, so I had to shorten up what I was doing. So we're going to take this probability. There's 10 in the sample. We're going to choose none on the default. Okay. We've got 0.113 at the 0 power. And then what I did was also I subtracted just so I would have less entries. So that's 0.887. So if you happen to do that, where all of a sudden you're trying to enter in a big string, this is failure, a big string of numbers or a big string of symbols and expressions, and all of a sudden I hit one more and it wouldn't let me enter anything, and I hit enter to see what happened, and it gave me an error message. And what I had done was used up all my places. So you may either do a little bit of arithmetic, so that's 10 minus 0 is 10, and do a little bit on the way, or lessen keystrokes, okay? I'm going to write all these down. 1.887. Let me make sure that's right. Yep, okay. 10 minus 1 is 9, so 9 plus 1 is 10. So 2 defaulted. So 10 minus 2 is 8. 8 plus 2 is 10. All right, and then we have that third one. Choose 3, 0.113 cubed. And then 10 minus 3 is 7. Okay. I actually could finally enter. You can enter that. You can put all of this plus all of this plus all of this plus all of this. Okay. I think if you do that, you may or may not run out of spaces. One of the things you might like to do is look at this and know that that's a 1, and look at that and know that that's a 1. That would definitely shorten keystrokes. Taking care of this would definitely shorten keystroke spaces. And I think that's probably good enough to get you in there. If not, I would recommend maybe either keying in 2 at a time and then adding the sum, or you could add the 3, get a total, and then do this one, add this decimal to the 3 that you calculated. So when I did that, I got 0.980484111. The first time I did this, I had a wrong value here and a wrong value here, and when I did my calculation, I was over 100%, so it was 1 point and a bunch of numbers, so I knew something was wrong. And I forgot to check that these add to the 10, and just made an error there. So if it can happen to me, it can surely happen to you. So there's that probability. So this one's a little funky. Let's switch it around and say at least 3 students defaulted on their loan. Okay, so at least 3 defaulted. So what that means is I've got 3, 4, 5, 6, 7, 8, 9, 10. So that's 8 of these that I would have to do. Okay, that's a little cumbersome. But if we can think about the complement, if I take 1 minus the one that we previous did, at most 3. So in numbers, this is from at least 3. This is x is greater than 3, but it's also got to be between, it's got to be 10. So it's got to be between 3 and 10. So there's those numbers I would have to list algebraically. This is at most 3, and remember this was x less than or equal to 3. Words are fine, okay? But if you think about this, if I do the complement of this, which is here, okay, and this is 3, not a decimal, what I want you to notice is that will help us. But notice we have just subtracted out 3. So this gave us the probability at 3, choose 3. This removes the probability, choose 3. So before I go off and add, or before I go off and subtract, I've got to add that 3 back in, because each one of these included the 3 and it got subtracted out here. So I've got to put it back in. So this is 1 minus 0.980, and I'm going to go ahead and put 48411 just for less error. And then I'm going to calculate the probability at 3, which is 10, choose 3, 0.113 to the 3rd power, 0.887 to the 7th power. Okay, so let's get that done. Could you enter all of this? Yes, you could. All in one fell swoop. So that's 0.094312499, and that's going to be about 0943. So that is at least 3 defaulted, okay, that percent. So at least about almost 9.5% defaulted of the 10 in the samples. So now, I think this one's hard. Makes you have to think. And it's dealing with this language here that makes that one a little bit difficult. So now we want to get to expected value. Remember, the cool thing is this is a binomial distribution. So we've got that nice little easy formula. Okay, so what is the probability of the number of defaults in our sample? So we had a number of 10. We had a probability of default at that, so that's going to be 1.33, or 1 point, oops, I wrote this wrong. This is 10 times 0.113, so that will be 1.13, and that is students. Don't lose sight of what you're finding. So in the long run, we would expect on average that 1.13 students will default on their student loans. Remember, this is kind of an average, okay? And that is binomial probability.